Lay down and make yourself comfortable. Close your eyes gently and let your mind settle. Let your body rest as your imagination drifts outward, beyond the familiar sights of your room, beyond the streets and trees, beyond your planet, outward into the vastness of space. Subscribe to explore a new documentary each evening and tell us where you're listening from. Quick question. What time is it where you are? Hold on. I've got one final question before we start. Imagine the stillness and the quiet. In that silence, one question rises naturally. If the universe is so immense, if the stars are so many, why have we not yet seen or heard anyone else? The universe stretches far beyond the reach of our eyes. When we look at the night sky, the stars seem like tiny points of light, scattered across the dark canvas, distant and calm. Each of those points may be a sun, similar to our own, and each sun may be surrounded by planets, some small, some large, some hot, some cold. Scientists estimate that there are more than 2 trillion galaxies in the observable universe. Each galaxy may contain hundreds of billions of stars. The numbers are so large that they almost escape the mind. Counting them, imagining them, fills the imagination with a sense of endless space and almost unbearable silence. The Milky Way, our home galaxy, is a spiral of stars, clouds of gas and dust. From Earth, it looks like a pale, glowing band across the sky, but in reality, it is immense. The Milky Way is about 100,000 light-years across. A light-year is the distance light travels in a year, nearly 6 trillion miles. Even at the speed of light, it would take 100,000 years to travel from one edge of our galaxy to the other. Within this galaxy alone, there may be hundreds of billions of stars, many older than our Sun, many younger, each with their own history and future. Beyond the Milky Way, galaxies appear as faint smudges of light, each one hosting countless stars. And beyond those galaxies, there are still more, stretching farther than we can see. The observable universe, the part we can measure and detect with telescopes, extends about 46 billion light-years in every direction. The true universe may be much larger, potentially infinite. The scale is difficult to imagine. We are tiny specks in a vast cosmic ocean, floating on a small planet around an ordinary star in a galaxy filled with billions of others. Distances in space are often measured in light-years because conventional units like miles or kilometers become meaningless at such scales. When we speak of a nearby star being 4 light-years away, that is about 24 trillion miles. The nearest star system to us, Alpha Centauri, is that far away. Even traveling at the fastest speed humans have ever achieved in space, it would take tens of thousands of years to reach it. Now, imagine traveling to other galaxies, millions of light-years away. The distances expand in ways that feel almost impossible, yet each star remains a point of potential life, a potential home, a potential observer. Time in the universe is as vast as space. Our Sun formed about 4.6 billion years ago, a middle-aged star in its life cycle. Galaxies formed even earlier. Some stars we see today were already ancient when Earth formed. Light travels across space slowly enough that when we look at distant stars, we see them not as they are, but as they were millions or even billions of years ago. A galaxy 10 million light-years away is seen as it existed 10 million years ago. The universe we observe is a record of its past, a chronicle frozen in light, revealing its immense history and gradual evolution. The universe is not static. Galaxies move, stars are born and die, Clouds of gas collapse into new suns, and planets form in swirling disks. Over billions of years, the universe changes in ways both dramatic and subtle. Stars explode as supernovae, scattering elements across space, building the raw materials for planets and life. Black holes grow in the centers of galaxies, shaping the motion of stars around them. The cosmic landscape is dynamic and ongoing, yet the scale and speed make it seem almost motionless to human eyes. Observing the universe requires tools and patience. Telescopes collect faint light that has traveled across space for millions or billions of years. Space telescopes, free from Earth's atmosphere, capture ultraviolet, infrared, and X-ray radiation invisible to human eyes. Each observation adds another detail to the map of the cosmos. Astronomers chart the position and motion of stars, measure the brightness of distant galaxies, and study the composition of interstellar clouds. Every new discovery confirms the immensity and complexity of the universe, making the silence of space even more profound. Within this grand expanse, Earth is a small planet orbiting a modest star in a quiet corner of one galaxy. Our planet is tiny compared to the universe, and yet it is the only place known to harbor life. The Fermi Paradox emerges from this perspective. The stars are so numerous, the galaxies so vast, that even if intelligent life were rare, there should be traces of it somewhere. Yet, as far as we can observe, the night sky is silent. No signals reach us, no visitors appear, no evidence of distant civilizations gleams in the light of distant suns. The contrast between the abundance of opportunity and the absence of contact forms the heart of the paradox. As we drift among these thoughts, imagining the universe stretching endlessly in all directions, the mind begins to sense the scale, not just in space, but in time. Civilizations, if they exist, may rise and fall, stars may live and die, and light from the furthest reaches of space may be traveling toward us even now, carrying messages we have no way to understand. The universe is full of possibilities, and yet, in this vast theater of matter and energy, we find ourselves alone in observation, gazing into the darkness, pondering the question, where is everybody? Even in the quiet of this thought, the enormity of the universe can be calming. The steady motion of stars, the slow unfolding of cosmic events, the grand architecture of galaxies spiraling silently in the void, all of it provides a sense of order and rhythm. The Fermi Paradox is not just a question, it is an invitation to observe, to calculate, and to explore, to understand the universe in its immensity and in the subtle dance of light and matter. It is the beginning of a long journey through facts, numbers, and the vast landscape of reality, guiding us to explore the reasons behind the silence and the possibilities hidden among the stars. We begin with numbers and scale, because understanding the size of the universe is the first step in grasping the mystery. It is only when we measure the stars, chart the galaxies, and contemplate the distances that the question becomes real. If there are countless worlds, countless chances for life, the absence of communication or contact is startling. Each star, each planet, is a potential answer to the paradox, yet the answer remains elusive. The universe is immense, and our curiosity stretches alongside it, patiently and quietly, like a light moving through the darkness, seeking and observing. Beyond the vastness of the universe, beyond the countless galaxies, each star has its own story. Stars are not all the same. Some are small and cool, burning slowly for tens or even hundreds of billions of years. Others are large and hot, burning brightly and rapidly, living for only a few million years. The size, temperature, and lifespan of a star shape the environment around it, determining the potential for planets to form and for life to take hold. Stars are not static points of light. They are furnaces of nuclear energy, producing the elements that make planets, oceans, and life itself. Hydrogen fuses into helium, helium into carbon, oxygen, and heavier elements, enriching space with the building blocks of complexity. The color of a star reveals its temperature. Blue stars are extremely hot and massive. White stars are moderately hot. Yellow stars like our Sun are medium, and red stars are cooler and often smaller. Each type of star creates different possibilities for planets. The largest stars burn quickly and may end their lives in violent supernovae, scattering elements across space, but leaving little time for life to develop on nearby planets. Smaller stars live longer and provide a stable environment where planets could maintain liquid water and steady conditions for billions of years. In this way, the type of star determines the potential window for life to emerge. Planets form from clouds of dust and gas surrounding young stars. These protoplanetary disks swirl and collide, gradually clumping into larger bodies. Gravity shapes these clumps into spherical planets. Some are rocky, like Earth or Mars. Some are gaseous, like Jupiter or Saturn. The distance from the star, the composition of the planet, and the stability of the star all influence whether the planet can hold an atmosphere, sustain liquid water, or develop conditions favorable for life. Even tiny differences in orbit or mass can make a planet barren or capable of supporting living organisms. In recent decades, astronomers have discovered thousands of planets beyond our solar system, known as exoplanets. These discoveries have changed our understanding of how common planets are and how varied they can be. Different methods reveal these distant worlds. The transit method observes tiny dips in a star's light as a planet passes in front of it, revealing the planet's size and orbit. The radial velocity method measures the subtle wobble of a star caused by the gravitational pull of orbiting planets, giving information about mass and orbit. Direct imaging captures faint light from the planet itself, though this is much harder due to the brightness of the star nearby. Each method adds pieces to the puzzle of the universe's planetary diversity. Exoplanets appear in many forms. Some are large gas giants orbiting close to their stars, called hot Jupiters. Others are small rocky worlds that may resemble Earth or Mars. Some orbit in tightly packed systems, some alone. Some have thick atmospheres, some thin or none at all. Observations suggest that planets are extremely common. Estimates indicate that most stars in our galaxy host at least one planet. When considering the stars in the Milky Way alone, there could be hundreds of billions of planets. This vast number increases the chances that at least some of them have the right conditions for life to exist. Among all planets, some lie in what scientists call the habitable zone, also known as the Goldilocks zone. This is the region around a star where temperatures are neither too hot nor too cold, where water can remain liquid on the planet's surface. Water is essential for life as we know it. Planets too close to a star may have water boiled away, while those too far may have oceans frozen solid. Within the habitable zone, a planet has a chance to support life, though many other factors such as atmosphere, magnetic field, and geological activity also play a role. Understanding the habitable zone helps astronomers focus their search on planets most likely to host living organisms. Stars are not solitary. Many exist in pairs or clusters, orbiting one another in complex patterns. This arrangement can influence the planets around them. In some binary systems, the gravitational pull of the second star can disturb planetary orbits, making life less stable. In others, stable orbits exist, and planets may experience regular cycles of light and warmth. Observing these systems allows scientists to understand the variety of conditions under which planets and potential life can exist, providing insight into the diversity of cosmic neighborhoods. The age of a star also matters. Young stars are often active, emitting strong winds and bursts of radiation that may strip away atmospheres from nearby planets. Older stars, like our Sun, are more stable, offering calm periods during which life can gradually develop. Stars eventually change, swelling into red giants or ending as white dwarfs or supernova remnants. The lifetime of a star sets the stage for how long a planet can remain hospitable. Longer-lived stars provide more time for life to emerge and evolve, whereas short-lived stars may offer only brief windows of opportunity. The discoveries of exoplanets in the habitable zones of their stars suggest that planets capable of supporting life are likely common in our galaxy. While we have not yet found direct evidence of life beyond Earth, the sheer number of candidate worlds makes the question of life elsewhere compelling. Planets with liquid water, stable orbits, and suitable atmospheres exist in numbers that are hard to imagine. Some may be similar to Earth in size and composition, orbiting stars much like our Sun. Others may be different in ways that challenge our ideas of what conditions are necessary for life, offering possibilities that expand the imagination even within strict scientific fact. As telescopes improve, we can study these distant worlds more closely. Instruments can detect the composition of exoplanet atmospheres, looking for gases like oxygen, methane, and carbon dioxide that might indicate biological activity. Light from these planets can reveal clouds, weather patterns, and surface conditions. With each new observation, we learn more about the environments that planets offer and how life might arise there. The study of stars and planets is a story of numbers, motion, chemistry, and the quiet unfolding of possibilities across the galaxy. It is a foundation for understanding why, in a universe so rich with stars and planets, we still face the question posed by Fermi. Why have we not yet encountered others who may exist among these distant suns? The presence of planets alone does not guarantee life. Life requires certain conditions, and the search for it begins with understanding what makes a planet capable of sustaining living organisms. Water is the most important ingredient. It is a medium for chemical reactions, a solvent that carries nutrients and allows molecules to interact. Without water, the complex chemistry necessary for life as we know it becomes almost impossible. Carbon is equally critical, forming the backbone of the molecules that make up cells, proteins, and DNA. Hydrogen, nitrogen, oxygen, phosphorus, and sulfur also play essential roles, participating in the chemistry that powers metabolism and growth. Energy is the third requirement. Stars provide light and heat, but chemical energy from minerals, volcanic activity, or chemical gradients can also drive life in the absence of sunlight. Together, water, carbon, and energy form the foundation for habitability, creating environments where life could take hold. On Earth, life exists in an astonishing variety of environments, many of which were once thought to be inhospitable. extremophiles. Organisms that survive in extreme conditions demonstrate the resilience and adaptability of life. Some bacteria thrive near deep-sea hydrothermal vents, where temperatures exceed 400 degrees Celsius and pressure is crushing. Others live in acidic lakes, with pH levels so low that most organisms would dissolve. Some survive frozen in ice for thousands of years, others in dry deserts with almost no water. Life has been found miles underground, inside rocks and in high radiation zones. These examples reveal that the boundaries for life are broader than previously imagined, expanding the possible environments on distant planets where life might exist. Timescales are also critical in understanding the emergence of life. On Earth, the planet formed about 4.5 billion years ago. The earliest evidence of microbial life dates to roughly 3.5 to 3.8 billion years ago, suggesting that life arose relatively quickly once conditions stabilized. Complex life, however, took much longer to develop. Multicellular organisms appeared over 1 billion years after the first microbes. The evolution of intelligence, capable of observation and technology, required further billions of years. In this sense, the timing of environmental stability and the duration of favorable conditions are crucial. A planet must remain habitable long enough for life to start and evolve to complexity, which narrows the list of planets that may host advanced civilizations. Scientists search for life on other planets by looking for signs called biosignatures. These are chemical markers in a planet's atmosphere, surface, or oceans that indicate biological activity. Oxygen, for example, accumulates in Earth's atmosphere due to photosynthesis. Methane can be produced by microbes in anaerobic environments. A combination of gases in unusual proportions may suggest ongoing biological processes. Detecting these biosignatures on distant planets is challenging. Telescopes measure the spectra of light passing through or reflecting off a planet's atmosphere. By splitting light into its component wavelengths, scientists can identify specific molecules. These measurements are subtle and require sensitive instruments, but each detected signal brings us closer to understanding whether life exists elsewhere. Life does not need to resemble Earth exactly. While our understanding is based on terrestrial biology, the discovery of extremophiles suggests that organisms may thrive in conditions very different from those on our planet's surface. Life might exist beneath the icy crust of moons like Europa or Enceladus, where oceans are shielded from harsh radiation. It could survive in the clouds of Venus or in the subsurface of Mars. By examining the extremes life can tolerate on Earth, scientists can expand their search, considering possibilities that were once dismissed as impossible. These insights guide the design of missions and telescopes aimed at finding life beyond Earth. Planetary atmospheres provide clues to habitability. The presence of water vapor, carbon dioxide, nitrogen, and other gases can indicate that a planet has the right conditions to support liquid water and, potentially, life. Temperature and pressure are determined by the composition and density of the atmosphere, influencing whether water can remain liquid. Some planets may experience greenhouse effects that warm them, while others may be too cold or too hot. Observing these conditions from light years away requires careful measurements and repeated observations, but they form the foundation of our understanding of habitability. Geology and planetary activity also matter. A planet with active volcanoes, tectonic shifts, and a magnetic field can recycle nutrients, stabilize the atmosphere, and shield the surface from harmful radiation. On Earth, plate tectonics help regulate carbon dioxide and maintain a stable climate over millions of years. Without such mechanisms, a planet may become uninhabitable even if it lies in the habitable zone. These factors, combined with chemical requirements and energy sources, create a complex but measurable framework for evaluating where life might exist in the cosmos. The emergence of life is not instantaneous. It is a gradual process that begins with simple molecules forming more complex chains. Over time, these molecules organize into structures capable of replication and metabolism. The process depends on favorable chemistry, stable environmental conditions, and sufficient energy. The earliest life forms were microscopic and simple, but they gradually altered their surroundings, changing the atmosphere and chemistry of their planet. This interplay between life and environment is detectable on a global scale, which is why scientists study atmospheric composition as a window into potential biology on distant worlds. Even with the right chemical ingredients, not every planet will host life. Random events such as asteroid impacts, fluctuations in climate, or the star's activity can prevent life from taking hold. But the sheer number of planets increases the likelihood that some worlds achieve the necessary balance. Life may be widespread, even if rare on any given planet. Each new discovery of an exoplanet with water or a suitable atmosphere strengthens the possibility that we are not alone, even as direct evidence of living organisms remains elusive. By combining the study of chemistry, energy, planetary conditions, and atmospheres, scientists can estimate the most promising places to search for life. This approach is grounded in observation and evidence, not imagination. It is based on what we know about life on Earth, the behavior of molecules, and the physics of planets and stars. Each factor adds a layer of understanding, building a map of the universe where life could exist. The Fermi Paradox becomes more intriguing in this context. We see many planets that could support life, some with conditions very similar to Earth. Yet the silence of the universe persists. The study of life's conditions is a bridge between numbers, observation, and the profound question of whether we are truly alone. After considering the conditions necessary for life, scientists began to ask a deeper question. How many civilizations in our galaxy might be capable of communicating across space? In 1961, Frank Drake formulated a way to estimate this number using what became known as the Drake equation. The equation is not a precise formula, but a tool to organize what we know and what we hope to learn about the likelihood of intelligent life. Each term in the equation represents a factor that influences the probability of civilizations existing and being able to communicate. Together, these terms provide a framework for thinking about one of the most profound questions in science. Are we alone? The first term in the Drake equation is the rate of star formation in the galaxy. Stars are the engines around which planets form, and the number of new stars born each year sets the stage for potential habitats. Astronomers have measured star formation in the Milky Way to be a few solar masses per year, meaning a few new stars, on average, appear each year. The second term is the fraction of those stars that have planets. Observations over the past decades, especially with missions like Kepler, suggest that most stars host planets, often multiple planets in a variety of orbits. Together, these first two terms establish the number of planets that could serve as potential homes for life. The third term considers the fraction of planets that could support life based on the conditions we just explored: water, suitable temperature, chemical elements, and energy sources. This term is more uncertain because we have only one example: Earth. However, studies of exoplanets and planetary formation give us clues about how many planets lie in their star's habitable zone and possess conditions that might allow life to develop. The fourth term is the fraction of those planets where life actually arises. Life may be common, like it appeared quickly on Earth, or rare, depending on how easily chemistry organizes into self-replicating molecules. Each possibility changes the expected number of life-bearing worlds dramatically. The fifth term of the Drake equation considers the fraction of planets with life that develops intelligence. Intelligence is more than simple survival. It includes problem-solving, planning, and awareness of the environment. Evolutionary biology shows that intelligence has arisen only a few times on Earth, which suggests it may not be inevitable, even if life exists. The sixth term addresses the fraction of intelligent life that develops technology capable of communication. Not every intelligent species may create radio waves, lasers, or other signals detectable across interstellar distances. Some may remain isolated, or their technology may not last long enough to reach other civilizations. The seventh term concerns the length of time such civilizations release detectable signals into space. A civilization that develops technology but quickly destroys itself may leave no trace for others to detect. Conversely, a long-lived civilization could send signals for millions of years, increasing the chance that someone else observes them. Each term in the Drake equation contains uncertainty, reflecting our incomplete knowledge of biology, planetary science, and sociology. Even small changes in one factor can dramatically change the final estimate of communicating civilizations. Probabilistic reasoning is central to the equation. Each term is essentially a probability, a fraction between 0 and 1, representing how common a factor might be. By multiplying the terms, scientists calculate the expected number of civilizations in our galaxy that could communicate. If one term is very small, it reduces the overall number. If several terms are close to 1, the number could be large. This reasoning allows us to explore different scenarios. Some scenarios suggest that intelligent life may be extremely rare, perhaps unique to Earth. Others imply that hundreds or thousands of civilizations may exist, even if we have not yet detected them. The historical context of the Drake equation is important. Frank Drake developed it not as a prediction, but as a framework for discussion at the first scientific meeting dedicated to the search for extraterrestrial intelligence. His approach combined astronomy, biology, and technology in a single equation, making the problem approachable and structured. Before this, discussions of alien life were speculative and unorganized. The equation gave scientists a common language to assess probabilities, to design experiments, and to measure progress in our understanding of the galaxy. It also sparked the development of the SETI program, dedicated to detecting signals from intelligent civilizations. Despite its usefulness, the Drake equation has limitations. Each term is uncertain, often estimated with wide ranges. The fraction of planets where life arises is unknown, and the fraction of intelligent life that develops detectable technology is speculative. The length of time civilizations release signals may be influenced by unpredictable cultural or environmental factors. Furthermore, The equation assumes a steady-state galaxy, ignoring dynamics such as star migration, supernovae, and galactic evolution that could affect the distribution and longevity of civilizations. While the equation is mathematically simple, the reality it tries to capture is complex, layered, and intertwined with unknowns. The equation also does not account for civilizations that use communication methods beyond our current detection capabilities. Advanced species may employ technologies we cannot recognize, or signals may be too weak or brief to observe. The equation focuses on detectable communication, not the total number of intelligent beings. In this sense, it is conservative and cautious, guiding our search without making unwarranted claims. Each factor reflects scientific reasoning, grounded in observations of stars, planets, and life, combined with educated estimates where data is lacking. It frames the discussion without asserting certainty, inviting continuous refinement as new discoveries emerge. Using the Drake equation, scientists can explore both optimism and caution. Even conservative estimates suggest that life may exist elsewhere, while pessimistic assumptions imply rarity or isolation. The equation is a reminder that our galaxy is vast and ancient, and that small probabilities multiplied over billions of stars can produce remarkable possibilities. It provides context for the Fermi Paradox. The numbers suggest that civilizations could exist, yet the silence remains. By breaking the problem into parts, the Drake equation transforms the abstract question of "where is everybody?" into a structured exploration of stars, planets, life, intelligence, and technology, giving each factor measurable or estimable properties that can guide observation and understanding. In practice, applying the Drake equation involves adjusting the terms as new data arrives. The discovery of exoplanets in habitable zones increases the fraction of stars with planets that could support life. Research on extremophiles influences estimates for the fraction of planets where life arises. Advances in astronomy refine the rate of star formation, and studies of technological development help consider how long civilizations might emit detectable signals. Each update brings us closer to an informed discussion about intelligent life, its distribution, and the chances of contacting others in the Milky Way. The equation remains a tool, a lens through which we explore our expectations, the potential for life, and the profound silence that continues to puzzle observers on Earth. Beyond the search for habitable planets and life itself, scientists look for signs that a civilization has developed technology. These signs are called technosignatures. They are evidence that a species has advanced enough to modify its environment or send signals that could travel across space. The most familiar type of technosignature is radio waves. On Earth, humans have been sending radio signals into space for more than a century. These signals can travel far, weakening as they move, but still potentially detectable over vast distances. Laser pulses, another possibility. A strong, focused beam of light could be used for communication across interstellar distances, producing a signal that could stand out against natural background light. Some theorists even imagine megastructures, large constructions around stars, which could alter the light we observe from distant systems. Each of these signs offers a way to detect intelligence indirectly through the effects it leaves on the cosmos. The search for extraterrestrial intelligence, or SETI, is a coordinated scientific effort to detect technosignatures. Since the mid-20th century, SETI has guided the search for life by looking for patterns in the radio waves from space that could indicate deliberate transmission. Early efforts used simple radio receivers, listening for unusual signals that could not be explained by natural sources. Over time, SETI expanded, incorporating new technologies, more sensitive receivers, and automated analysis. The goal is not only to find intelligent life, but also to measure how common technological civilizations might be in the galaxy. Modern SETI projects operate with sophisticated instruments and computer analysis. The Allen Telescope Array, for instance, is a group of radio dishes in Northern California designed to scan the sky for artificial signals. By observing many stars at once, it increases the chance of detecting a message or pattern that differs from natural noise. Breakthrough. Listen, launched in 2015, is one of the largest initiatives using some of the world's most powerful telescopes to study 1 million stars, the center of our galaxy, and nearby galaxies. It examines a wide range of frequencies, looking for narrow-band signals or pulses that could indicate deliberate transmission. Each observation involves analyzing vast amounts of data, searching for patterns hidden in the background of natural cosmic signals. Technosignatures are not limited to radio waves. Scientists also study light from stars for irregular dimming or brightening that could indicate artificial structures such as large solar collectors or orbiting panels designed to capture energy. Changes in the infrared spectrum could suggest waste heat from large-scale technological activity. Even small deviations in a star's light curve could hint at advanced engineering. These methods are subtle and require precise measurements, as natural phenomena can mimic artificial patterns. The search is like listening to a whisper in a hurricane, requiring patience, careful observation, and rigorous testing to avoid false positives. Detecting technosignatures is challenging because signals weaken with distance. A civilization broadcasting intentionally to the galaxy would need enormous energy to reach other star systems. Signals from ordinary planetary activity, like routine communication on another world, would be faint and intermittent, likely undetectable at great distances. Earth's own leakage of radio signals has become weaker over time as communication shifts to cable, fiber, and satellite systems that do not emit widely into space. This suggests that even if civilizations exist, they may not produce signals strong enough for us to observe, adding another layer of difficulty to the search. Background noise complicates detection. Cosmic phenomena, such as pulsars, quasars, and natural radio emissions, create a constant hum of energy across the sky. Distinguishing a technosignature from this natural noise is a major challenge. Advanced algorithms and computer systems scan the data for unusual patterns, repeating signals, or narrow frequency bands that do not match known astrophysical sources. Each candidate signal must be carefully examined, and often repeated observation is necessary to confirm its origin. False positives are common, caused by human-made satellites, radar, or terrestrial interference, making the verification process slow and meticulous. Despite these challenges, the potential reward is immense. Detecting a technosignature would confirm that intelligent life exists elsewhere, reshaping our understanding of our place in the universe. Even unsuccessful searches provide valuable information, helping refine techniques, focus efforts on promising targets, and improve sensitivity. SETI's work has grown into a collaborative international effort, with observatories around the world participating, data shared openly for study, and volunteer projects involving the public in analyzing signals. Each step increases the likelihood of success, even if the search remains long and uncertain. Techno-signatures also highlight the limits of our perspective. Our methods assume that other civilizations use technology in ways we can recognize. Signals may be continuous or brief, narrowband or broadband, intentional or unintentional. Civilizations could communicate in ways completely unknown to us, or signals could be directed along paths we cannot observe. We may be searching at the wrong frequencies, at the wrong times, or for the wrong type of signal. The universe may be full of signs of intelligence that are simply invisible to our current instruments. Understanding this limitation is part of the scientific process, guiding improvements in technology and observation strategy. In addition to radio and light-based signatures, scientists consider chemical signs as techno-signatures. For example, industrial pollution, unusual atmospheric chemicals, or synthetic compounds in a planet's atmosphere could indicate technological activity. Observations using spectroscopy can detect these features, offering another indirect method to search for civilizations. Each method adds a layer of evidence, providing a multifaceted approach to the problem. No single observation is definitive, but together, these measurements build a map of potential technological activity across the galaxy. The search for techno-signatures is an ongoing experiment, informed by the Drake equation, the study of stars and planets, and knowledge of the conditions for life. It connects astronomy, biology, physics, and engineering in the pursuit of a single, profound question: are we alone? The silence so far is notable, creating the puzzle known as the Fermi Paradox. Observations suggest that habitable planets and potentially life-bearing worlds are common, yet techno-signatures remain elusive. Understanding the difficulties of detection, from signal weakness to timing and interference, helps explain this absence while maintaining hope that one day a detectable sign may appear. Until then, the search continues, patient, methodical, and grounded in observation, as telescopes sweep the sky and computers analyze signals, seeking a whisper of intelligence among the stars. Among the many questions that scientists ask about life in the universe, one stands out for its simplicity and depth. Where is everybody? This question was posed by the physicist Enrico Fermi in the early 1950s during a conversation about the possibility of extraterrestrial life. Fermi's point was clear. If intelligent civilizations are common in our galaxy, if planets suitable for life are numerous, and if life itself can arise under the right conditions, then the galaxy should be teeming with civilizations. Yet, despite our searches and our observations, no evidence of these civilizations has been found. The question captures a paradox. The universe appears hospitable for life, yet the signs of other intelligent beings remain absent. Fermi reasoned that a civilization capable of space travel could colonize a galaxy in a surprisingly short time, at least in cosmic terms. Even with slow spacecraft, moving at a small fraction of the speed of light, the Milky Way could be explored or settled within a few million years. Galaxies are old, many billions of years older than Earth, providing ample time for civilizations to emerge, develop technology, and expand. If life and intelligence are not extremely rare, some civilization should have reached us, or at least left observable traces long before humanity appeared on Earth. This line of thinking turns the abundance of stars, planets and habitable worlds into a puzzle. We expect contact, but it does not occur. The implications of no contact are profound. Either intelligent life is far rarer than our calculations suggest, or civilizations do not expand in ways that leave detectable signs. Perhaps life frequently emerges, but rarely evolves intelligence. Perhaps intelligent species develop technology, but choose not to communicate or explore. Perhaps civilizations destroy themselves before achieving long-term stability or interstellar travel. Each of these possibilities carries its own consequences for how we view ourselves in the universe. The absence of observable civilizations forces us to confront the fragility of life, the limitations of technology, and the vast scales of space and time that govern cosmic events. Fermi's question also highlights the contrast between probability and observation. Mathematical estimates, like those derived from the Drake equation, suggest that civilizations should be numerous. Probabilities multiplied over billions of stars and planets indicate that some intelligent life should exist and some signals should reach Earth. Yet, when we observe the sky, using radio telescopes and other instruments, we detect silence. This tension between theoretical expectation and empirical evidence is the essence of the Fermi Paradox. It reminds us that understanding the universe requires both calculation and careful observation, and that nature may be more subtle than simple probability predicts. The paradox encourages careful thinking about assumptions. When calculating probabilities, we assume that civilizations behave in ways similar to humanity, or that life develops on timelines similar to Earth's. These assumptions may not hold. A civilization may not seek interstellar travel, may communicate in ways we cannot detect, or may exist for a period too short to overlap with our observation window. Even in a galaxy full of life, timing, technology, and behavior could conspire to keep civilizations hidden from one another. Fermi's insight was that the lack of contact is not proof of absence, but it is a challenge that demands explanation. Fermi's question also directs attention to the importance of scale. The distances between stars are vast, and light, radio waves or other signals take years, centuries or millennia to travel even modest distances. A civilization located hundreds or thousands of light years away could be transmitting signals that have not yet reached Earth, or that arrived in the distant past before our technology existed to detect them. The galaxy is a dynamic place, and civilizations may rise and fall on timescales that make synchronous contact unlikely. The universe's size makes the absence of observed contact less surprising, even if intelligent life exists elsewhere. The reasoning behind the paradox is logical and compelling. If intelligent life develops and survives, expansion through colonization is feasible. Even gradual colonization at speeds far below light speed could cover the galaxy in millions of years. Once a civilization establishes a foothold on a single planet, resources could support further expansion. Technologies like self-replicating spacecraft could multiply the reach of a civilization, spreading across star systems with minimal ongoing effort. These scenarios illustrate why scientists expect the galaxy to contain visible evidence of life, and why the continued silence intensifies the paradox. Despite these calculations, observation remains the ultimate test. Astronomers scan the skies, listening for signals, searching for anomalies in starlight, and examining the characteristics of planets and moons. So far, no verified technosignatures have been found. This silence does not mean life does not exist. It means either it is rare, hidden, or operates in ways beyond our current understanding. The paradox reminds us that nature may be subtle, and that human perception and technology are limited compared to the vastness of space and the potential diversity of life. Fermi's question resonates because it is both simple and unsettling. It challenges our assumptions about life, intelligence, and technology. It forces us to consider not only the likelihood of life elsewhere, but also the behaviors, longevity, and detectability of civilizations. It is a bridge between theoretical reasoning, like the Drake equation, and empirical investigation through observation. It is a reminder that science seeks not only to calculate probabilities, but also to confront reality, and that reality often defies expectation. In the quiet of space, with billions of stars and planets stretching across light years, the question lingers. If intelligent life is possible and the galaxy is vast, why have we not yet met anybody? The paradox endures as a central puzzle in the search for our place among the stars. In trying to explain the silence of the universe, scientists consider the possibility that life is extremely rare. This idea is often called the rare Earth hypothesis. According to this view, while simple life may be common, the combination of conditions needed for complex life is unusual. On Earth, many factors have aligned to make our planet habitable for intelligent species. A stable star, the right distance from it, a protective magnetic field, plate tectonics, a large moon to stabilize rotation, and a suitable atmosphere are just some of these factors. Even small changes in any of these could prevent complex life from developing. The rare Earth hypothesis suggests that while planets exist in great numbers, those that meet all the necessary criteria for intelligent life may be few, making our existence exceptional in the galaxy. Another idea is the concept of the Great Filter. This theory proposes that somewhere along the chain from simple matter to advanced civilization, there is a stage that is extremely hard to pass. It could be the emergence of life itself, the development of intelligence, the ability to build technology, or the survival of civilizations long enough to communicate across the stars. If the Great Filter is behind us, it means that we are rare survivors of an improbable series of events. If it is ahead of us, it implies that advanced civilizations tend to destroy themselves or fail to survive long enough to spread. Either way, the Great Filter explains why, despite the vast number of habitable planets, the universe appears silent. It frames the absence of contact as a consequence of difficult steps in the development of intelligent life. Life on Earth appeared relatively quickly after the planet stabilized, but intelligence took billions of years to emerge. This long timescale introduces another explanation: timing. Civilizations may rise and fall on cosmic timescales that rarely overlap. Stars and planets have existed for billions of years, far longer than humanity. Some civilizations may have already appeared and vanished long before humans existed. Others may emerge millions of years from now. In this view, the galaxy may host many intelligent species, but the periods during which they are detectable could be brief compared to the age of the cosmos. We may exist in a moment between the rise and fall of countless civilizations, observing a temporary silence that will change over time. The interplay of rarity and timing creates a complex picture. Even if habitable planets are relatively common, the steps from simple life to advanced Communicating civilizations may involve improbable events. Each stage, from the formation of organic molecules to the development of technology, may be highly sensitive to local conditions and chance events. The longer it takes for intelligence to arise, or the more fragile it is once it does, the fewer civilizations exist simultaneously in the galaxy. This could explain why the numbers suggested by the Drake equation do not match what we observe. The probabilities of life and intelligence may be multiplied across the vastness of space, but the final result may be small due to the fragility of each step. Rare Earth also considers the stability of environments over time. Planets may experience catastrophic events such as asteroid impacts, supernova explosions, or runaway climate changes. Life may emerge repeatedly, but civilizations capable of technology may be wiped out before they can communicate. On Earth, life survived 5 major mass extinctions, each of which could have ended the evolutionary trajectory that eventually produced humans. On other planets, these or similar events may prevent intelligent life from ever arising or sustaining itself long enough to be detectable. Stability, combined with rarity, may limit the number of civilizations present at any given time. Timing extends beyond individual planets to the galaxy itself. Stars are born and die, and their planets evolve with them. Some planetary systems may have had habitable zones for only a brief period. A civilization arising too late or too early relative to these windows might never reach the point of interstellar communication. Likewise, civilizations may emit signals for a finite time, either because they evolve beyond detectable technologies or because their societies collapse. When signals are brief in cosmic terms, the chance that another civilization observes them is low. Timing therefore acts as both a filter and a source of apparent silence, adding a temporal dimension to the search for life. The Great Filter and Rare Earth hypotheses also suggest a sense of fragility in life's development. Even minor disruptions could prevent progress beyond simple organisms. Intelligent species may be particularly vulnerable to environmental changes, resource depletion, or self-inflicted disasters. The longer a civilization exists, the more likely it is to encounter challenges that threaten its survival. This fragility may explain why, even if life is common, we have not yet detected other intelligent beings. The paradox is not a contradiction, but a reflection of the delicate balance required for advanced life to exist and endure across time. Understanding these explanations requires an appreciation of the vast scales involved. The Milky Way is over 100,000 light-years across, with hundreds of billions of stars. Each star hosts its own timeline and planetary system. Civilizations may arise on different stars at different times, separated by distances and intervals that make contact improbable. Even if many civilizations exist or have existed, the chances of coinciding in both space and time may be small. The combination of rarity, fragility, and timing may produce the appearance of a silent galaxy, even in a universe rich with possibilities for life. The concept of rarity is strengthened by Earth's example. Our planet's combination of factors that support complex life is precise and delicate. The survival of life through catastrophic events, the long timescale required for intelligence, and the ability to develop technology have all been highly contingent. In this sense, Earth may be unusual, and intelligent civilizations may be exceptionally rare. Timing adds another layer, emphasizing that the galaxy's history is long dynamic, and not synchronized with human observation. The absence of contact is not evidence that civilizations do not exist, but rather that the conditions for life and the periods of detectability are constrained and uncommon. In considering the rare Earth and great filter explanations, scientists gain insight into why the galaxy appears quiet. These ideas suggest that intelligent life may be a fleeting or fragile occurrence, that the steps from simple chemistry to advanced civilization are improbable, and that civilizations may rarely overlap in time. While the universe offers countless opportunities, the combination of environmental stability, chemical readiness, evolutionary chance, and temporal alignment may limit the number of civilizations capable of interstellar communication at any given moment. Silence, in this context, becomes a natural outcome of probability, time, and the delicate processes required for life and intelligence to emerge and persist. The universe is a vast and often dangerous place. Even planets with the right conditions for life can face hazards that make the survival of civilizations difficult. Stars can explode as supernovae, releasing enormous energy that can sterilize nearby worlds. Gamma-ray bursts, rare but extremely powerful, can deliver lethal radiation across thousands of light-years. A planet situated too close to such events may have its atmosphere stripped away or life extinguished entirely. Asteroid impacts, large enough to alter climate or disrupt ecosystems, are another natural threat. Earth itself has experienced several mass extinction events caused by such impacts. While life has often recovered, intelligent species may not survive, or may arise only intermittently, limited by these catastrophes. Planetary instability can also pose challenges. Volcanic eruptions, earthquakes, and shifts in climate can disrupt ecosystems for long periods. Ice ages and global warming events shape the evolution of species and the stability of civilizations. A technologically advanced species may develop the means to counter some dangers, but large-scale or sudden events could still threaten existence. Even planets with seemingly perfect conditions are not immune to these hazards. Survival requires both resilience and adaptability, qualities that may not be common among intelligent civilizations. Self-destruction is a concern that adds to cosmic hazards. Civilizations capable of technology may also create tools of war, extract resources unsustainably, or inadvertently alter their climate. Nuclear weapons, chemical or biological hazards, and artificial intelligence, if mismanaged, could endanger a species on a planetary scale. Even without deliberate catastrophe, technologies that support civilization can produce unintended consequences. Environmental degradation, resource depletion, or societal collapse may shorten the period during which a civilization exists and is detectable. The universe may be full of civilizations that rise and fall too quickly for contact to occur. The longevity of a civilization is closely tied to its visibility. A species that exists for only a few hundred years may produce radio or light signals detectable only briefly. Long-lived civilizations, surviving thousands or millions of years, would be more likely to produce observable signs. Earth has been transmitting radio waves for just over a century, a tiny fraction of cosmic time. If other civilizations have similar or shorter lifespans, the chance of overlapping periods of detectability with humanity is low. Longevity is therefore crucial for the possibility of contact, and short-lived civilizations may explain much of the apparent silence in the galaxy. Cosmic challenges also influence the spread of civilizations. Even if a species develops interstellar travel, natural hazards can hinder expansion. A ship moving between stars faces radiation, gravitational hazards, and the risk of collisions with interstellar debris. Long journeys may require technology that preserves life for centuries or millennia, which may be difficult to achieve. Civilizations that survive locally may never attempt or succeed at spreading across the galaxy. The combination of external dangers and technological limits constrains the observable footprint of intelligent life. Civilizations that do survive long periods may still choose isolation. Awareness of cosmic dangers could lead to deliberate caution, limiting signals or avoiding contact with unknown species. Even with advanced technology, the risks of communication or exploration may outweigh potential benefits. This behavioral factor intersects with natural and self-inflicted hazards to reduce the likelihood that civilizations are both widespread and detectable. Silence may be an outcome of prudence as well as circumstance, reflecting survival strategies rather than absence. Intermittent catastrophes also play a role. A planet may recover from an asteroid, impact, or climate upheaval, allowing life to evolve anew. Intelligent civilizations could arise multiple times, each lasting only a short span before ending. In a galaxy billions of years old, civilizations may have appeared and vanished countless times without leaving detectable traces. The temporal spacing of emergence and extinction events adds complexity to the search for life. Observation at a single moment in time may capture a quiet interval between civilizations rather than a permanent absence. The interaction of cosmic hazards and self-destruction underscores the fragility of technological species. Even favorable conditions for life do not guarantee longevity or detectability. Each civilization exists within a narrow window where survival, technology, and communication align. Beyond this window, they may disappear or cease to be observable. The galaxy may host many planets with life, yet only a few civilizations may reach the stage where their presence can be measured across interstellar distances. This pattern explains why we might expect numbers from probabilistic reasoning, but find a silent sky in practice. Understanding these challenges helps reconcile the Fermi Paradox with the observed universe. Natural events, combined with the fragility of intelligent civilizations, create a situation where life may be common, but detectable technological civilizations are rare. Each hazard, from gamma-ray bursts to self-inflicted disaster, adds to the difficulty of survival and visibility. The universe may be full of life in varying forms, but the combination of dangers and the limited duration of detectable signals makes contact extraordinarily unlikely. Our observation of silence does not contradict the potential abundance of life. It highlights the constraints imposed by the harsh realities of the cosmos. The scientific study of these hazards informs the search for life. Astronomers monitor nearby stars for supernova candidates, survey planets for geological stability, and analyze atmospheres for signs of extreme environmental changes. Understanding how catastrophes impact habitability helps refine expectations for where civilizations might exist. It also emphasizes the importance of looking for long-lived signals and considering the timing of events on cosmic scales. By integrating knowledge of natural and technological risks, scientists can better model the likelihood of detecting intelligent life and interpret the emptiness of observed space as a complex outcome of survival, timing, and hazard. Considering cosmic challenges frames humanity's perspective. Earth has survived multiple natural disasters, and humans have developed technology that both threatens and protects our existence. The awareness of these hazards reminds us of the fragility inherent in intelligent life and the narrow window of opportunity to communicate or explore. The combination of external dangers, self-destruction, and the temporal limits of detectability illustrates why the universe may appear silent despite potentially numerous civilizations. Cosmic challenges shape the probability of contact, offering a scientific explanation for the enduring mystery of the Fermi Paradox and emphasizing the delicate balance required for civilizations to persist long enough to be observed. The Fermi Paradox reaches beyond numbers and observations, touching the way humans think about themselves and their place in the universe. If intelligent life is rare, or civilizations are often brief, then the existence of humanity carries profound significance. Earth may be a unique refuge of intelligence in the galaxy, and the responsibility of preserving and understanding life becomes central. This perspective encourages careful reflection on how humans interact with their planet and with each other. It suggests that the decisions we make now about technology, environment, and social systems affect not only our survival, but our opportunity to participate in the wider cosmic story. In this context, the universe is both vast and quiet, and our presence is a remarkable result of many delicate and fortunate circumstances. The ethical considerations of contact or isolation are intertwined with the paradox. If civilizations exist, should humanity attempt to communicate actively, or should we remain quiet? Broadcasting messages into space could reveal our location to unknown civilizations, with potential benefits or risks. Some argue that contact could advance knowledge, culture, or technology. Others caution that the consequences are unpredictable, suggesting restraint and careful study before making deliberate transmissions. Even if no contact occurs, the ethical responsibility extends to our treatment of life on Earth, as we may be one of the few, or perhaps the only, civilizations capable of reflecting on these questions in the galaxy. The paradox also guides scientific methods and search strategies. Understanding that civilizations may be rare, brief, or difficult to detect informs how astronomers allocate resources and design observations. Surveys focus on regions with higher probabilities of habitable planets, examine stars with long lifespans, and employ sensitive instruments capable of detecting faint or brief signals. Studies of exoplanets, atmospheres, and planetary stability provide data that refine models of life and intelligence. This approach demonstrates a careful balance between optimism and realism, acknowledging the vastness of space while recognizing the limitations of our technology and observational windows. Astrobiology is central to the discussion. Studying the chemical and environmental conditions required for life informs expectations about where intelligence might emerge. Research on extremophiles and the resilience of life on Earth suggests that life can exist in a wide range of environments. But complex life requires stability and long timescales. Planetary protection becomes important as we explore other worlds. Robotic and human missions must avoid contaminating extraterrestrial environments, both to preserve potential ecosystems and to ensure that observations of life are accurate. Protecting planets from human influence maintains the integrity of the search and respects the possibility of independent life elsewhere. The search for life and intelligence encourages global collaboration. Sharing data, telescopes, and analysis tools allows scientists worldwide to contribute to the study of the galaxy. Projects like Breakthrough Listen and SETI engage researchers in systematic, long-term efforts to scan the sky. By coordinating observations, using multiple wavelengths, and developing advanced detection methods, scientists increase the chances of finding signals or anomalies that may indicate intelligence. The paradox motivates innovation, combining astronomy, biology, technology, and ethics in a single scientific pursuit. It shapes the questions we ask, the instruments we build, and the approaches we take in exploring our cosmic neighborhood. Humanity's reflection on the paradox also has philosophical dimensions. The absence of detectable civilizations challenges assumptions of universality, suggesting that intelligence may not be inevitable or permanent. It prompts questions about purpose, survival, and the meaning of observation. The quiet of the galaxy contrasts with the abundance of stars and planets, emphasizing the fragility of existence and the rarity of civilizations capable of reflection and technological development. These considerations influence the way society values knowledge, preservation of life, and careful stewardship of technology and environment. Ethics and philosophy extend to potential discoveries. If evidence of life, even microbial, is found, how should it be treated? Planetary protection guidelines emphasize caution, avoiding interference that could harm alien ecosystems or compromise scientific study. Similarly, if technosignatures are detected, decisions about response, communication, and disclosure require careful ethical and social consideration. Scientists must weigh the benefits of interaction against the uncertainties of consequences, taking responsibility for actions that may have interstellar implications. The paradox encourages foresight, prudence, and reflection, emphasizing that science is intertwined with human values and decisions. Refining search strategies also involves prioritizing targets based on habitability and stability. Stars with long lifespans, planets in stable orbits, and systems with conditions conducive to complex life are emphasized in observational planning. Techniques include monitoring for periodic signals, spectral analysis for atmospheric biosignatures, and detection of anomalies in starlight that could indicate artificial structures. By combining probabilistic reasoning with empirical observation, scientists improve the likelihood of success while acknowledging the limitations imposed by distance, time, and technology. The paradox serves as a guide, reminding researchers to consider both possibility and likelihood in their search for life. The Fermi Paradox informs humanity's perspective on its own future. Recognizing the rarity and fragility of intelligent life underscores the importance of sustainability and long-term planning. It encourages investment in technologies and strategies that enhance resilience, from planetary defense against impacts to management of climate and resources. It also inspires curiosity and wonder, motivating the study of stars, planets, and the processes that make life possible. The paradox, in its silence, offers both a challenge and an opportunity. A challenge to understand why the galaxy appears empty, and an opportunity to reflect on our responsibilities as one of the few known intelligent civilizations, shaping our destiny with awareness of the fragile and precious nature of life in the cosmos. The Fermi Paradox challenges humans to think about themselves in ways that are both quiet and profound. When we consider the possibility that intelligent life is rare in the galaxy, it places Earth and its inhabitants into a special position. Our planet may be one of the few, or even the only, worlds where intelligent observers have evolved. This realization can inspire a sense of humility and wonder, as well as a recognition of responsibility. Earth is not just a home. It may be a rare sanctuary for life capable of reflection, curiosity, and understanding. Considering this uniqueness encourages humanity to treat the planet and its ecosystems with care and thoughtfulness, as mistakes could have consequences not only locally, but for the continuation of intelligence in the cosmos. The idea of rarity also affects how we view our own achievements and potential. The evolution of intelligence, the creation of technology, and the development of complex societies are results of precise and delicate conditions. The same processes that allowed humans to observe the stars could have failed on countless other worlds. Each step in our evolution, from the emergence of multicellular life to the development of language, reasoning, and scientific thought, represents a narrow path through chance and circumstance. This understanding frames human life as both extraordinary and fragile, highlighting that intelligence is not inevitable, but a product of time, stability, and opportunity. The quiet of the universe emphasizes this fragility, reminding us that survival and progress are not guaranteed. Ethical considerations arise when contemplating the possibility of other civilizations. If intelligent life exists, should humans attempt to contact it? Broadcasting messages into space carries unknown risks. A civilization may be benevolent, indifferent, or hostile, and any attempt at communication could have consequences that cannot be predicted. Some argue that sending messages could foster interstellar cooperation, leading to shared knowledge or cultural exchange. Others suggest caution, emphasizing the potential dangers of revealing our location and technological capabilities. Even the decision to remain silent requires ethical reflection. Choosing not to transmit signals protects humanity and respects the uncertainties inherent in cosmic contact. Silence, in this sense, is itself an ethical choice, guided by prudence, foresight, and awareness of our limitations. Isolation has philosophical implications that extend beyond practical concerns. The possibility that humanity exists alone in the galaxy or within a very sparse community of civilizations prompts questions about purpose and meaning. Does the universe seem empty because intelligence is uncommon, or because our ability to detect others is limited? The silence challenges assumptions of universality, forcing us to confront the idea that being alive and capable of thought may be rare and precious. These reflections influence cultural, scientific, and personal perspectives, inspiring both curiosity and a sense of responsibility. Humans are observers of a vast and quiet cosmos, and that role shapes the questions we ask, the knowledge we seek, and the value we place on life. Philosophical reflection extends to the stewardship of life on Earth. If intelligence is uncommon, our responsibility to preserve and nurture life becomes greater. Environmental protection, sustainable technology, and careful societal planning take on cosmic significance. Each choice that affects the stability of civilization or the survival of ecosystems is amplified by the possibility that humans are one of the few civilizations capable of reflection. The silence of the universe encourages mindfulness about resource use, technological development, and the avoidance of self-destructive behaviors. Ethical decision-making becomes not just a matter of social or national concern, but a consideration in the continuity of intelligent life itself. The paradox also raises questions about human communication and curiosity. Our desire to explore, to send messages, and to understand the cosmos is part of what defines intelligence. But reflection on the silence of the galaxy tempers the desire with caution. Even as we develop radio telescopes, space probes, and observation satellites, we must recognize that our attempts to connect could carry risks we cannot fully calculate. Philosophical insight comes from understanding both the power and limits of technology. Knowledge of the vast scales of space and the fragile nature of life encourages a careful approach to exploration, emphasizing both ambition and restraint. Humanity's perspective is influenced by the timescale of the universe. Stars and planets exist for billions of years, far longer than the span of human civilization. In this context, our species is young and brief. Civilizations elsewhere, if they exist, may have risen and fallen long before humans existed, or may arise far in the future. The realization that we are part of a temporary window of observation and action deepens the sense of both responsibility and wonder. Each observation, each scientific discovery, is an effort to understand a universe that is far larger and older than ourselves. Silence in the galaxy encourages reflection on the transient nature of civilizations and the fleeting opportunity for contact or exploration. The philosophical implications also touch on meaning and purpose. If we are alone, or nearly so, the significance of human experience increases. The search for knowledge, the study of life, and the pursuit of understanding become not just a local or cultural effort, but a contribution to the awareness of the universe itself. Human consciousness may be among the rare forms capable of contemplating existence on a galactic scale. This perspective can inspire awe, humility, and a careful consideration of how our actions resonate across time and space. The quiet cosmos becomes a mirror, reflecting both the rarity and potential of intelligence, and emphasizing that our choices have importance beyond immediate observation. Ethical reflection extends to future generations. Humanity must consider how technology, culture, and policy affect the survival and development of intelligent life. Planning for resilience, sustainability, and continuity ensures that our species can continue to observe, understand, and potentially communicate across the galaxy. Philosophical insight derived from the Fermi Paradox encourages long-term thinking, fostering a sense of stewardship not only for Earth, but for the possibility of life as a whole. The choices we make now influence our ability to participate in the broader cosmic narrative, and silence in the universe reminds us that opportunity is not guaranteed. The Fermi Paradox invites contemplation of responsibility and care. Understanding that intelligent life may be rare highlights the ethical, philosophical, and existential dimensions of human existence. We are observers, custodians, and participants in a universe that may rarely produce beings capable of reflection. Our actions, both technological and cultural, shape the potential for life and intelligence to endure. Awareness of our unique position encourages careful thought, deliberate planning, and ethical consideration. In a quiet galaxy, humanity's perspective gains depth, and the recognition of rarity and fragility fosters both humility and purpose, guiding our choices and inspiring continued reflection on our place among the stars. The Fermi Paradox not only raises philosophical questions, but it also shapes the way scientists plan the search for life and intelligence beyond Earth. Understanding the rarity of intelligent civilizations encourages a more strategic approach. Instead of looking randomly across the galaxy, astronomers focus on stars and planetary systems that are most likely to host habitable planets. Systems with stable stars, planets in the habitable zone, and low likelihood of catastrophic events become priority targets. This targeted strategy maximizes the chance of detecting life or technological signals while considering the limitations of time, distance, and equipment sensitivity. Hazards and cosmic dangers also guide the selection of observational targets. Stars that are too young, too old, or prone to violent activity may not support long-term stable life. Gamma-ray bursts, supernovae, and extreme stellar flares can sterilize planets or shorten the window for civilizations to develop detectable technologies. By factoring in these risks, scientists refine search criteria, prioritizing regions of the galaxy where life could have persisted long enough to reach intelligence and develop technology. This approach combines probabilistic reasoning with empirical data, creating a realistic framework for the search for extraterrestrial civilizations. The timing of civilizations is equally important. Signals from intelligent life may be rare, because civilizations arise and disappear on timescales that rarely overlap with humanity. Long-lived civilizations have a better chance of being observed, so searches focus on stars and planets that have been stable for billions of years, allowing for the gradual evolution of life. Observing systems with sufficient time for complex life to emerge increases the likelihood that a civilization might exist, and that any signals, technological or otherwise, are still detectable. In this way, the study of stellar and planetary evolution informs the design of observational campaigns. Astrobiology benefits directly from these considerations. Research on extremophiles, organisms that survive in extreme conditions on Earth, provides clues about the potential adaptability of life. Scientists investigate how life might exist under high radiation, low temperatures, acidic conditions, or extreme pressures. These studies expand the range of environments considered potentially habitable, guiding searches for life on exoplanets and moons with unusual characteristics. Planetary protection principles emerge from this work, ensuring that human exploration and robotic missions do not contaminate fragile ecosystems, either to preserve native life or to maintain the integrity of scientific observations. Planetary protection also addresses the challenge of observing life accurately. Contamination could compromise experiments or lead to false conclusions. Strict guidelines prevent forward contamination, introducing Earth microbes to other worlds, and backward contamination, bringing extraterrestrial organisms to Earth. These precautions preserve the credibility of astrobiological research and reflect the ethical responsibility associated with discovering life beyond Earth. The combination of protection, careful planning, and long-term observation ensures that the search for life is both scientifically rigorous and ethically sound. Collaboration among international teams is essential. No single observatory or country can scan the entire galaxy or analyze every possible signal. Sharing data, coordinating observations, and developing standardized methods increase the likelihood of detection. Projects like Breakthrough Listen and SETI exemplify this approach, using radio telescopes, optical instruments, and advanced software to monitor thousands of stars over long periods. Global cooperation allows the scientific community to cover more ground, integrate findings, and adapt strategies based on new information. The paradox itself motivates this collaboration, encouraging researchers to pool knowledge and resources in pursuit of answers to a question that spans the galaxy. Technological innovation drives progress in the search for life. Instruments capable of detecting faint signals, analyzing atmospheres for biosignatures, and imaging exoplanets are continuously improving. The development of more sensitive radio arrays, high-resolution spectrographs, and space-based observatories increases the range and precision of observations. Advances in computational analysis, machine learning, and simulation allow scientists to model planetary environments and predict where life may arise. Technology shapes the effectiveness of the search, allowing humanity to probe deeper and more accurately into the cosmos, despite the challenges posed by distance and faintness of potential signals. Long-term observation is crucial. Civilizations may emit signals intermittently or for only brief periods, so persistent monitoring increases the chances of detection. Continuous or repeated observation over decades and centuries may eventually capture signals missed in shorter studies. Similarly, studying exoplanets and their atmospheres over extended timescales helps identify transient changes that could indicate life. Patience and consistency are fundamental in a field where detection relies on rare, faint, or brief phenomena. The search is a gradual, careful process, reflecting both the vastness of the galaxy and the rarity of civilizations capable of communication. Scientific methods are continually refined based on outcomes and discoveries. Each non-detection provides data that adjusts probabilistic models, informing expectations and guiding future searches. Understanding the limitations of instruments, recognizing sources of interference, and developing strategies to detect weak or complex signals are all part of an iterative process. The Fermi Paradox frames these challenges, reminding scientists that absence of evidence is not evidence of absence, but it also calls for improved approaches and critical evaluation of methods. Continuous refinement allows the scientific community to pursue the search with increasing efficiency and insight. By integrating knowledge of rarity, hazards, timing, astrobiology, and planetary protection, humanity can direct its search for life with focus and responsibility. Long-term observation, technological innovation, and international collaboration expand the chances of detecting civilizations or life beyond Earth. The paradox teaches that silence is not merely emptiness. It is a signal about the constraints and challenges of life and intelligence in the galaxy. Each step in refining our methods brings humanity closer to understanding the vast, quiet cosmos and our role within it. The combination of careful planning, ethical responsibility, and scientific insight ensures that our efforts are both thoughtful and effective, reflecting the profound lessons that the Fermi Paradox offers about life, civilization, and the universe. As we reach the final thoughts of this journey through the Fermi Paradox, it is helpful to pause and consider the scale of what we have explored. The universe is vast beyond human imagination, filled with billions of galaxies, each containing billions of stars and countless planets. Despite this immense number of worlds, the cosmos remains quiet. The silence is not simply empty space, but a reflection of the complexities and challenges of life, intelligence, and communication across such distances. We have seen how stars, planets, and environmental conditions influence the emergence of life, and how fragile intelligence may be in the face of cosmic hazards and self-inflicted dangers. The enormity of time and space adds layers to this silence, reminding us that civilizations may rise and fall in intervals far longer than our human perspective. This awareness does not diminish the wonder that fills the cosmos. On the contrary, it enhances it. The vastness of space, the countless possibilities for life, and the delicate processes that have produced our own civilization invite a deep sense of curiosity and awe. Each star is a potential world, each planet a potential cradle for life. The quiet of the universe encourages reflection on the rarity and significance of our own existence. Humanity, perched on a small planet in a quiet corner of a galaxy, is given the unique opportunity to observe, explore, and contemplate the vastness that surrounds it. This perspective fosters both humility and inspiration, reminding us that our curiosity is a bridge between the known and the unknown. Ongoing exploration is a central part of this story. Observatories scan the sky, spacecraft journey to distant worlds, and scientists analyze data to search for the faintest signs of life or intelligence. These efforts are patient, careful, and methodical, reflecting the long-term nature of the task. The process itself, even without a confirmed discovery of extraterrestrial intelligence, teaches us about the universe, about planets, stars, atmospheres, and the potential for life under many conditions. In studying the cosmos, humanity gains knowledge, perspective, and a deeper understanding of its own place in the grand scheme of existence. The search is both scientific and philosophical, linking curiosity with reflection. The silence of the galaxy can also be soothing when considered with care. Knowing that we are observers of an immense, mostly quiet universe allows space for contemplation and calm. The cosmos does not demand immediate answers or actions. It encourages patience, wonder, and acceptance of mystery. The knowledge that life may be rare or fleeting, and that communication may be improbable, invites a gentle, reflective appreciation of our own world. The quiet becomes a backdrop for thought, for imagining possibilities, and for embracing the beauty of a universe that is still largely unexplored. In this way, understanding the Fermi Paradox can be calming as well as enlightening. Reflecting on the galaxy also reminds us of the preciousness of life. Earth has provided the conditions for intelligence to develop, and humanity has reached a stage where observation, reflection, and exploration are possible. This recognition highlights the responsibility inherent in our position. Caring for our planet, preserving the diversity of life, and using technology wisely become acts that resonate not only for our species, but potentially for the broader understanding of life in the universe. Each moment, each choice, becomes meaningful in the context of a galaxy that may rarely produce observers capable of such thought. In quiet contemplation, one can imagine the universe as a vast ocean of possibilities, with stars as islands and planets as small, fragile worlds where life may flicker and fade. Some civilizations may have appeared long ago, others may exist far away, and still others may rise in the future. Humanity occupies a moment in this grand timeline, able to look outward and consider the immense space, the deep silence, and the delicate conditions required for intelligence. This perspective blends scientific insight with philosophical reflection, emphasizing both the vastness of what is unknown and the uniqueness of our ability to observe and reflect upon it. The act of searching itself becomes a form of understanding. By looking for techno-signatures, analyzing atmospheres and monitoring stars, humanity engages with the universe in a meaningful way. Even if no other civilizations are ever detected, the endeavor provides knowledge, context, and insight into planetary systems, the formation of stars, and the processes that govern life. The journey of observation and discovery enriches human perspective, offering a quiet satisfaction and a sense of purpose. Exploration and study are ways to connect with the cosmos, to appreciate its scale, and to recognize our small but significant role within it. As the mind settles into reflection, one can imagine lying beneath the night sky, noting the stars and the possibilities they hold. Each point of light is a reminder of both what we know and what remains unknown. The calm awareness of the universe's vastness encourages introspection and serenity. Thinking about the Fermi Paradox, the silence, and the rare conditions that allow life to flourish can inspire awe and patience. It is a quiet understanding that the universe is ancient, immense, and still largely hidden. Yet within it, humanity has the capacity to observe, wonder, and learn. This contemplation nurtures both a sense of peace and a gentle curiosity that can accompany sleep. In conclusion, the Fermi Paradox leaves us with a gentle and thoughtful message. We may never hear from other civilizations, and yet the search for life and intelligence is a profound way to engage with the cosmos. Observing the stars, studying planets, and reflecting on the conditions for life allow humanity to understand its place in the universe. The silence is not emptiness, but an invitation to wonder, to curiosity, and to contemplation. As you rest, letting the mind drift among the stars, it is comforting to know that even in quiet, the act of looking and thinking connects us to the vast, mysterious universe. We may never hear from them, but the search itself is a way to understand our place in the universe.